Hello, and welcome back again to our continued exploration of the details of the synthesizable subset of Verilog. Now we're going to look at continuous assignment. I've done continuous assignment right after doing operators because the way continuous assignment is used is that the right-hand side is constructed from operators. You cannot have behavioral code such as if, else's, and case statements in a continuous assignment statement. In contrast, procedural code is sometimes referred to as behavioral logic description because you can describe behavior such as using a case statement to represent a truth table. So here, the basic idea is that the statements are executed whenever anything on the right-hand side changes. That's why it's called continuous assignment. And of course, you will recall that all variables assigned this way must be of type while or try. The try is actually relatively rare. We'll illustrate the only use of try in synthesizable code in a moment. So in this particular example here, D is the output of a 2-bit output of two 2-to-1 AND gates, and E are two muxes side by side, with B0 being the select line. So let's look at a simple example here. Here, on the left-hand side, we concatenated carry and sum together to produce a 5-bit variable that's assigned to the 5-bit output of this adder. Question is, what is the structure that is being specified here? And I want to point out very specifically that the parentheses are important here to get the structure as intended. This is the structure that is described here. D colon B C is producing a selector, which is then one of the operands of a adder, which produces a 5-bit output, the 5th bit being the carry out, which we've just given a different name, and that's the value of using this concatenation together. You can have different variables concatenated together, even though the logical unit produces a specific width output. I want to note that if I didn't have the parentheses here, the result would be very different because of the precedence rules. You might recall the item with the lowest precedence is $:. Thus, what this would be building would at least attempt to build, would be a multiplexer with A plus D going to the select line. This would actually be a syntax error since the selector here has to be 1 bit and A plus D is multiple bits. So it would be very different, and in fact a syntax error, if we left out the parentheses. The only way to implement tri-state buffers to in turn implement a shared bus is using continuous assignment with a try data type. So here what we are doing is using the $:: logic to select onto A either a variable or a signal or a net, or the high impedance state. You might recall in the Verilog 2.1 notes, we looked at the high impedance datum, and what it means is disconnected. So what this is doing is at any one time, one of these, of B or C, is connected to the tri-state bus. The other one is in the high impedance state, that is, it is disconnected. And you might recall we looked at the transistor structure of a tri-state driver back then. So this is what we're specifying here. Again, B and C are now tri-state drivers. That is, the outputs have 3 states, 1, 0, or high impedance. The 1 or 0, of course, comes from the input B or C. Notice that this is designed very explicitly so that only one of these tri-state buffers is driving the bus at any one time. This is very important because if you have more than one unit driving the tri-state bus, then you'll get collisions on this bus, and you'll get indeterminate logic values on it, both in simulation and in the actual final hardware, and this will lead to logic errors. Notice this is the only time in Verilog, in synthesizable code in general, that you can assign a variable from two different places. And the only reason we can do that in this case is because of the use of high impedance, to make sure that only one of these structures is actually driving the bus F at any one time. So this is the only way to build a tri-state buffer and a shared bus in synthesizable Verilog. There is a data type called tri-reg, which is not synthesizable. I do discourage you from using tri-state buses in your design. Generally, these are higher order structures intended to connect large logical units together in a controlled fashion. And they're actually quite complex because of this requirement that only one unit can be driving the bus at any one time. That means you need an arbiter of some sort to decide who gets to own the bus on a particular clock cycle. So this can get quite complex and quite difficult to get right. So I do discourage you from using it in small designs such as you're doing in this class. However, there is one exception, and that is some FPGAs have lots of tri-state buffers within them, which you can actually use as a mux. And in fact, that's actually how I've coded this. If this was the only pair of buffers driving this tri-state unit, this is essentially configured as a mux. Again, I don't encourage you to build muxes this way. Build them the more straightforward way. However, we'll talk about this again in the FPGA section. This forces FPGAs to actually use all their tri-state buffers more productively. Here's some more examples of operators and continuous assignment. And here I'm illustrating some common data logic structures. These are all combinational logic, of course, because there's no pos-edge clocks. Here's some data logic structures that are actually quite useful in general design. We've actually seen a couple of these before. First one here, B equals curly bracket AA shifted right C. You can see what we're doing here. The behavior on the right hand side is we're concatenating A with itself and shifting right C units. C will only be up to 4 because C is only 2 bits wide. So the question is here, what is the logical structure that we're specifying? And it's a rotator. What I mean by that is it's taking the value A and rotating it right C bits. By rotating, I mean as it shifts to the right, the low order bits of A, instead of disappearing, get shifted in to replace the missing high order bits. So it's not zero filled, but filled with the low order bits of A. Let's look at how the behavior of this code, remember behavior implies function, leads to this being recognized as a description of a logical rotator. So remember what we're doing here is we're taking the 4-bit variable A, making a copy with itself on the left, shifting that right C bits. So for example, if C was 2 on one particular clock cycle, it'd be shifted right 2 bits. That is, A2 would now be the low order bit in the shifted result. B is only 4 bits wide. So if you assign a wider variable, a wider vector to a narrower vector, you only get the low order bits. Well, now the low order bits are A1 to A2. So B becomes equal to these 4 bits. That is, we specified the rotator. That the high order bits have been replaced by the low order bits A1 and A0 instead of zeros. This would be a logical rotator. Again, there are no registers here because there's no pos-edge clocks. And this is one of the beauties, of course, of synthesis. We did not have to consider at all how to design this internally. In fact, logic optimization would produce a reasonable result for the combinational logic that creates a general rotator. Of course, C is also an input to the rotator, the number of bits being rotated. D, let's look at what we're doing here. We're building 4 copies of A, concatenating that with itself and shifting that right E bits. E is only 2 bits wide, so only shifting to the right 4 bits. Well, this is building a signed right shift. That is, in a very similar way to the rotator, by putting 4 copies of the sign bit to the left of A, any shift will preserve the sign bit and furthermore sign bit fill the vector that's been shifted. So the general structure is a signed right shift unit. Finally, down here, we're taking a 2-bit variable B, using that as an index to the 4-bit variable A and assigning that to the 1-bit variable C. But what we're building here is a multiplexer, because B is selecting one of the 4 bits of A to be assigned to C. And this is a very, very shorthand way to build a multiplexer from that takes a vector as an input and produces a 1-bit result. So that brings us to the end of this short section on continuous assignment. It allows you to take expressions using the operators to create actually quite complex structures sometimes, but they're very efficient to capture. This doesn't involve much typing at all, which is the beauty of using continuous assignment. I remind you that this is the only way to build tri-state muxes and shared buses, though I do discourage you from using such structures because they can get quite complex. And of course, all variables assigned continuously must be of type wire or type trie. I now encourage you to go into the submodule quiz before proceeding to the next module. Thank you very much.